No. It revolves around three things. The drawings, actually being able to draw what it is, being able to tell the distance between them, right? The standard equation, L equals inland over 2, or if it's closed in one end, over 4, right? And then only odd harmonics then. And the wave equation, velocity equals wavelength times frequency. Those are the three things that all these problems revolve around. To get this first one here, an organ pipe open on both ends, right, automatically tells me which equation am I going to want. L equals open on both ends.
N lambda over 2.
Good, over 2. And lambda over 2, right, not over 4. 4 is closed on one end. Okay. How long is the pipe? First off, I can solve for length here, right? I can solve for length here. If I knew wavelength, how can I get wavelength? V equals lambda f, right? V equals lambda f. Velocity of sound in air is approximately 340, right? Approximately 340. And organ pipes, last time I checked, produced sound. So 340 lambda, let's make that a little bit better, times 280 hertz, right? What wavelength does that give me, please? What wavelength does that give me? 1.21? 1.21 meters approximately. If we were drawing a picture of what's going on here, just because you don't have to have a picture for this, but there are other problems in your homework that kind of depends upon the picture. Like there was a little table in there that talked about what's the distance from the first node to the second antinode and all that. That's completely picture dependent. So I mean, let's actually draw a picture just so we can make sure we're feeling good about this. Open on both ends, right? The fundamental looks like what? Yeah, it's two antinodes, right? So, ooh, that's terrible. Try this again here. That's a little bit better, right? Two antinodes, half the wavelength, right? That's why n being 1 divided by 2 is half the wavelength. Okay. So now I take this, plug it in, right? And solve. L equals 1 times 1.21 divided by 2. L equals what? 0.605. I get how many sig figs? 2, so 0.61. 0.61 meters. Okay.
The equation not happening.
Nope. It all comes from the drawing. Certain things aren't in the packets. This is not the packets. It's kind of standard. Know what's happening inside pipes and strings or standing waves. In worst case scenario, though, if you forget it, you can always go back and derive it. And the way to derive it is the exact same way as what we did. I guess it was yesterday or the day before that, where we actually drew out, closed on both ends or open on both ends, and then just started drawing the harmonics in there and saying how much of a wavelength is this, and we solved the half of the same figure out the question. So worst case scenario, go back and get it on that one. Next, what's the frequency of the third harmonic? This is just working backwards through what we've already done, right? Start out with L equals n lambda over 2, so that's 0.61 equals the third harmonic, wavelength divided by 2. Lambda equals what, please? 0.404. Keep a few extra sig figs right here. Don't care about to the end. How do I get the wavelength to the frequency? Yes, velocity wave equation. Right, so that's 340 equals 0.404 times F. Frequency equals what? 840. Unit, please. Hertz. You are not promised, by the way, you're not promised this to actually be broken out into 2 steps for you. You're not promised this to actually be broken out into 2 steps for you. This could be The information from the first problem, right? The information from the first problem, and then the second problem is the question. It could go something along the lines of an organ pipe is open on both ends and has a fundamental frequency of 280 hertz. What is the frequency of the third harmonic? I gave you the in-between step needed. Find the link first. Okay, I gave you the in-between step. Find the link first. You are not promised that. Okay, in fact, you're promised right now the opposite. Right? I'm almost promising you that I will not give you the in-between step on the test, nor will the IB exam. Okay? You just need to know, hey, I've got the fundamental frequency, right? With the fundamental harmonic, I can use that to get over to the length of the pipe. Once I know the length of the pipe, I can solve for any harmonic I need. Okay? You need to know that. You need to know that. You also have to know the difference between closed on both ends, open on one end, open on both ends. Okay, you need to know the difference between them. Cool? Questions? Yeah.
Are the equations the same for open on both ends, closed on one end, and closed on both ends? It's just in the closed on one end, you only have odds.
Odds and it's divided by 4.
Odds.
Yes, odds is divided by odds, closed on one end divided by 4. Open on both ends and closed on both ends are the same. Great.
Closed on one end. If you did like an even, like algebraically, what is that showing? Like, what is that number?
If you did, you're saying closed on both,
Like
closed
if you
on one
plugged
end.
in 2 or 4.
It's physically impossible. It's physically impossible, and that's a good question. But here's the reason why. Pipe closed on one end, right? You can only come out with 1/4 of a wavelength, 3/4 of a wavelength, 1/4 wavelengths, right? That's 5/4, right? And so on, so on, so on. It's impossible to get an even number. Let's say 2/4, 1/2 of a wavelength. I can't fit that in with the conceptual rules that there has to be a node there, and there has to be a antinode there, right? There's no way physically to draw that and come out with just half of the wavelength. It's either going to be, a fourth, right? Or you can get 3/4, right, of a wave. But you can't get half. That's why the evens aren't allowed here. I guess mathematically you can shove it in, right? But understand, math was created for physics, right? Math was created to explain the world around us, aka physics, right? Physics wasn't created for math, right? So there are mathematical things you can do that don't work in the real world. Right? This would be one of them. Equations that go with this. Please use the equations found in your packet, not in the book. Please use the equations found in your packet, not in the book here. The book equations are right. They're not incorrect. Okay? They're just not as simplified as they should be. So equations that I want you to use. F prime equals F. F prime being the new shifted frequency. The apparent frequency that you've got. Okay? F prime equals F, the actual frequency, times V over V plus or minus US. This is for a moving source. That's for a moving source. Plus or minus means moving away and moving towards. And you have to actually choose which one to use here.
Is it US?
U sub S. U sub S. V stands for the velocity of the wave, right? If we're dealing with sound, the velocity of sound, whatever medium you're dealing with, generally it's about 340 meters per second. Okay, if we're dealing with velocity in air. By the way, the velocity in air changes greatly depending upon the temperature. Right, changes greatly depending upon the temperature. If the air is colder, that means it's more dense. That means the wave is able to travel quicker. Okay. So we get there. Which, by the way, band folks, also changes the sound whenever you come to being sharp and flat. But anyway,
tracks.
Correct.
But that would make your instrument sharper because it makes it shorter when it tracks. But you get flatness.
You also have the effect of the speed of sound increasing too.
But that's stronger than contracting it. It's kind of thinking about before.
Here. I haven't run the experiment. That'd be an interesting one to run. Right? In fact, mathematically, Banthos, next time you're out in cold play, right, actually do the calculations for how much it contracted, right? And I can give you equations to do that. Compare that to, running this through, lambda, to what the velocity of sound must be. So see which one changes most. Just, a thought, something to chew on, how to figure out how to run that experiment. That'd be a good thing to do. Now let's figure out what I want to use, plus or minus here. If the source is coming towards you, you're the listener, you're stationary, the source is coming towards you. You'll want to use a plus or a minus, right? You want to look at the frequency whenever the thing is coming towards me. Does the frequency go up or does the frequency go down? It goes up, right? Frequency goes up when the source is coming towards me. So this U sub s is in the denominator. If U sub s was 0, right, this would be V divided by V, 1, right? To get this thing to become greater than 1, this entire thing in parentheses here, this entire thing in parentheses is kind of a multiplication term, right? It becomes a constant that we're multiplying frequency by. Do you want to subtract off the V or add to the V? Subtract. I want to subtract. Here's why. V divided by V is 1. V divided by anything less than V, right, is going to give me 1 point something, right? 1 point something. For example, with sound, let's say you're 340 divided by 340 minus 40. It becomes 340 divided by 300, which is 1 point something, times F gives me a higher F prime. The opposite works too, right? If you're going away, you're going to want to add. You're going to want to add. Make that entire multiplication term there some decimal number, something less than 1. Okay?
What is U?
U stands for the velocity of the source. Velocity of the source. We've used U for initial velocity in the past. Now, if this source is accelerating, this is a different ball game. Okay? If the source is accelerating, it's a different ball game. That means U is constantly changing. Right? That means doppler shift is constantly changing. So we're not going to be dealing with a changing velocity here. Okay? We're going to deal with constant velocity of the source. All right, and the other equation here for a moving listener, F prime equals F, not another equal sign.
Wait, moving source or moving listener?
Now I'm doing moving listener. V,
What is U?
U is the velocity of the guy, U sub S, velocity of the source. Now UO, velocity of the observer, okay, velocity of the observer. V is the velocity of the wave. Lots of times here we're talking about sound, which would be 340 meters per second, but it doesn't have to be sound, okay? And by the way, we can put that sound in different mediums, water, things like that, which changes the V, okay? All right, this equation is for a moving observer, moving observer, okay? The same effect will happen, Doppler effect, if you are in your car. Oh, yes, thank you. Plus or minus U sub O, or velocity of the observer. The same effect happens, okay, for Doppler effect, if the police car is driving towards you and it passes you and goes away from you. The same effect happens if the police car has a siren going and sitting on the side of the road, and you're driving towards him, and then you pass him, right? Whenever you're coming at him, you are naturally hitting more waves more often, right? Because you are running into them, right? And whenever you get to the other side, you're running away from them. So you're naturally only going to have to hit you less often. The frequency will go down. So here, figuring out a plus-minus situation, when you're going towards, do you want the frequency to go up or down? Up, so I don't want to use plus or minus. Plus. It's in the numerator now. When I'm going away, I want the frequency to go down, so I would use minus. The two equations in black also telling you when to use them, source and observer, are given to you in your packet. What is in red is not. You have to know that. Emily.
Okay. I'm a little confused about like when you're saying like if a police car can still when you're going by. Because if you're going at the same speed the whole time, then you think that you just use the waves to.
Okay. It's a good question. I haven't taken much time to explain it. I don't have a great applet for it, but we'll come back and figure it out here.
So when you're going forward, nothing else. The waves are going this way, in an opposite direction. And then
Now,
going the other way, where you're going.
let's see if we can't come back to this and get this to explain it.
And chase down the national
Small load. Whenever you're going towards it, what you're going to find is even though that object is sitting still, because you are going towards it, you are hitting the waves more often. And whenever you're going away from them, you are running away so they hit you even less often. If you will, while this loads up, think about being in the ocean. All right, think about being in the ocean. And there are two different times where you experience a doppler effect, if you will, whenever it comes to ocean waves. Whenever you run out into the ocean, right? Now, this is a moving source, and this, excuse me, there wouldn't be a moving source here. The source of the waves is just out in the sea, right? For imagination's sake. And then you have water waves coming at you, okay? Whenever you run out into the ocean, the observer, and you're running in there, do the waves hit you more frequently or less frequently? More frequently. Right? You're running in the opposite direction. The actual source isn't moving, it's sending out waves, right? But since you're running in the opposite direction, the waves hit you more often, right? You get hit and you run a little bit, you get hit again, you run a little bit and you get hit again. On the other hand, whenever you've been out in the ocean for a little while, it's time to come in, you turn around and you run back in. You're running the same direction as the waves are going, right? You, the observer, are hit more or less often. Less often. In fact, if you're like me, whenever I'm doing that, after I finally get enough out of the water, right, to where I can pick up a little bit of speed, the goal is to beat the wave that's right behind me into the shore, right, to where I don't get hit at all, right? That's the idea. It's just fun. Right. The frequency goes down a lot whenever you're going the same direction as the observer. You're running away from it at that time. Apparently this is not going to load back up.
I guess it makes sense that you miss some waves because you're outrunning them or whatever, but you still doesn't it make any sense what I'm saying? If you have a bunch of lines and you're running into them, and you're still going to hit the same amount of lines that are in front of you. You're just not going to get hit by the ones that are behind you.
Yes, you're going to get hit by the same amount. Well, let me see if I can draw this out since this wasn't working. But it's not about how many you hit. Here's a source putting out sound waves in a spherical band, right? No big deal. It's not about the frequency. It's not about how many of the waves you hit, which, by the way, sound waves are just always coming out. Okay? This is just trying to use pictures to talk about it, so we're having to deal with pulse waves, just to talk about it. But it's not about how many you hit. It's frequency, how many you hit per unit time. Per unit time. Okay? So whenever I'm coming this way, right, whenever I'm coming at it, I am, and the waves, like waves are coming at me, right? What is the net speed, the apparent speed? Well, it's a lot greater. It's a lot greater. Okay, these guys are hitting me, right? These guys are coming to hit me, and I'm running into them. So how much does time get reduced before I hit the next wave? A decent amount, depending on how fast I'm going, right? Because not only is the wave coming at me, I'm also going at it. So it takes less time to get to the next wave. Thus the frequency goes up, right? On the other side, though, now the waves are going this way, right? And I'm going the same way. Now here, with sound waves, you're not going to run at the speed of sound, right? That's where our ocean example breaks down. The waves are still going to hit you, but you are running the same direction as the waves. You're trying to run away from them. Now they're going to overtake you eventually, but since you're trying to run away from them, you are prolonging the time. You're lengthening the time it takes before the next wave, if it was pulse waves, would hit you. So the frequency would go down the other side. That was a really good one there. Yes?
How much of a change in frequency can you achieve by speeding up? Changing velocity?
Let's do a problem. All right, you want moving source or moving observer? Moving observer, sure.
Source.
Okay, we'll do
I had an
a
idea. I want to do moving source. And it's the first that I had.
okay, we'll do a moving source. You want the source coming towards us or away? Towards. Okay, so let's have a police car. And I'll just draw this out. Police car with one big red light. Okay, one big red light coming at you, and here you are over on the side. You know, here's Camden, all happy, over here on the side, and the police car is coming at you. Hopefully not to arrest him, but to go get someone else. Right? Police car is coming at him with a velocity of, I mean, cars, they're going to go 35 meters per second. Okay?
So I guess that would be if you're going 340.
We'll get there.
No, that would be one. Oh, so you can change the frequency by one.
We'll get there. Let's start out with just a basic one, and then we'll go to the extremes, because I see where you're going. It's a lot of fun whenever we get to the extremes. He's going 35 meters per second towards Camden, right? Producing sound at, oh, let's say 415 hertz. Producing sound waves, you know, sound at 415 hertz. Do I know exactly what pitch that is? Not off the top of my head, but I wrote down 400 and some odd yesterday a few times whenever, you know, we had instruments playing, so it's about 400 hertz. Okay, so 415 hertz. What is the frequency Camden hears over? What's the frequency that Camden hears? How'd you get it? You used, because it was coming towards the minus sign, right? Minus 35, right? And I need to come back in here. We need to insert in our actual frequency now. 415, and so you heard an F prime of what? Give me that again, Ken. 400 and what? Should go. 4 what? 462? Unit place. Hertz.
Could you do like 1 over negative 35? Is that English chemistry?
1 over negative 35 times 415? No. Oh, that will not give us traction. Yeah, the trick here is this entire thing, this 340 minus 340 times 35, it becomes a multiplication constant, right? It's got, think about units. In the numerator, what is its units? Meters per second. In the denominator, what is its units? Units cancel out, giving us this unitless multiplication factor. Right. Plug in 340 divided by 340 minus 35. This should come out to be 1 point what? Unitless multiplication constant, right? Saying we are going to multiply 415 by this constant 1.115. Right.
How do you over meters per second as well? Because there's one meter per second.
All right, so let's actually work this problem with units. Okay. Let's just do this conceptually here in mathematics. First step would be to do 340 minus 35, right? So this becomes 340 meters per second divided by 340 minus 35 equals what? 305 what? Meters per second. When adding and subtracting, we have to have the exact same units, and then the units persist. 305 meters per second. Now, whenever I'm dividing, what happens to those units? They cancel out. So that was a good question. Right, so whenever I'm dividing, I'm going to get the units to cancel out. Okay. So that problem was just the basic plug chug style. That was just the basic plug chug style. Let's go one step up just for a tangent, because this sounds like he wants to have fun with this. And let's say, just for the sake of argument, that our police car is no longer going 35 meters per second. Let's put them up at 300 meters per second. Dang booking, okay? But this is way faster than is possible. No, I mean, getting a car that breaks the sound barrier has been a big deal, all right? I think we have, we've done it, but it's not like
We have like two giant jet turbines.
Yeah, it just doesn't happen much, right? So NASCAR doesn't touch this, okay?
No.
But we're going to do it for the sake of mathematical argument, right? So now I've got F prime equals, I said it was producing at 415, right? 415 times 340 minus 340, let's see, 340 divided by 340 minus 300. What does this F prime come out to be? Before you even give me F prime, give me this multiplication constant, please, and then give me F prime. 8.5. 8.5. And so F prime comes out to be 3527. Not worrying about sig right here. Now, conceptually think about this. Just the multiplication constant. As my speed grows, as I approach 340, what happens to that multiplication constant? It gets bigger, and bigger, and bigger, and bigger, right? So, if we were dealing with limits here, right, and that would be a term that you're going to get familiar with in math. Limit just means as you approach something, as we get closer to it, what would be the limit of this possible idea, right? What happens whenever I get closer and closer to 340? What does that constant go to? What goes to 0, right? 340 minus 340 is 0, right? But imagine not getting all the way there. Imagine plugging it now 339.999. What happens? Oh, this is going to be 340. This would be 340 divided by 0.001, right? It'd be all bigger, times 10 to the third, right? Now, let's do it again. 339.9999 becomes what? 340 times 10 to the 4th, right? And every time that I get closer, I'm going towards what number? Infinity. Infinity. Yes. Yes. This is the idea of the limit, and you'll get familiar with this. Okay, it just means what happens as you approach. Keep plugging in numbers that are closer and closer and closer. What happens as you approach it? What's going to happen is this constant is going to go to infinity. Infinity times this frequency means that as you get closer to the actual speed of sound, frequency goes up to possibly infinity. Where, mathematically, infinity is just this conundrum, right? When actually you hit the sound barrier, this equation breaks down, right? Because you can't have an infinite frequency. It breaks down, and thus, all the sonic boom stuff. That's different. Okay.
Do you know what the change in frequency between two radically adjacent pitches are? because
No.
it's not consistent.
It's not consistent.
So I was thinking you could like form a song by moving a vibrating string closer, and I mean a different velocity, like come towards you at once and then it goes
Yes, you
up.
can, because at any time, you can hit, looking at this, by changing the speed, right, you can hit any frequency you so choose. All the way up to infinity, and all the way down to whatever that actual one is, except that you start going the other way. So all the way down to 0. You can hit any frequency you so choose. All right, let's work one other problem here.
Like,
10 seconds. Okay.